Hey class, so here's a video for the last homework problem, number 56 from chapter 9, and I thought I'd just try to help you guys get started. So in this problem you can see here that we're really dealing with a couple different points in time or situations. So as you can see, there's going to be what I'm going to call point 1, which is right here, right before the collision occurs. So car B is moving, car A is stationary, and they're just about to collide. Then I'm going to call, or insert, I guess, a point 2, which we'll put right here, which we're going to call right after the collision. So at point 2, you have car A that's now moving with some new velocity, right? I'll call it v2 for car A. And you also have car B, maybe my color should have been the other way, but, well, let's move that here, sorry. So you also have car B that's just impacted car A, so it's right here, and it too is moving with V2B after the collision. It's going to be moving slower than it started, but it's still going to be moving. And then we have over here point 3 in time shown here, which is when they've both moved. Alright, and we can see that the velocities of both of them at point 3 are 0. So what you're going to need to do here is you're going to have to look at what happens from point 1 to point 2. What do we got going on? Well, we have a collision. We're even given a hint in the problem statement. That's nice. Don't expect that to always be there. But we're told that momentum is conserved. So that means that our momentum at point 1 must be equal to our momentum at point 2, and we only have x direction motion, so the x momentums must be equal to each other. That's good. Okay, and then we're looking at point 2 to point 3, and we have the two cars sliding, so for that we're going to look at, or I'm going to choose to use, conservation of energy. And you can use equations of motion and forces and things as well, but I like using energy, so I'm going to go with conservation of energy between those 2 points. Okay, so let's look at what that would look like. So first, if you're working forward, starting with point 1, you'd say, okay, well, I have momentum initial, so my initial momentum would just be the mass of car B multiplied by the initial velocity of car B. So we'll call that V initial, since that's what it's labeled in the picture, and that's what we're trying to find in part C, I believe. And then that's going to be equal to our momentum right after the collision, which would be mass A times V2A plus mass B times V2B. So that's our conservation of momentum equation. So to find our initial velocity, which we're asked in part C, we first need to know V2A and V2B. Okay, and so to get that, we're going to come down here and use conservation of energy. Alright, and so in this case we can break down the cars one at a time. Alright, so maybe I'll use color coordination here. So we got car A. So with car A, it starts with 0 kinetic energy, 0 potential energy, so all it has is work being done by non-conservative forces, which is friction, and that's going to be equal to all it has right, oh wait, sorry, I said that backwards. Excuse me, let's erase that. So we do have kinetic energy when we start, right? We end with 0 energy. So we have initial kinetic energy, that was close, minus work done, or plus work done by non-conservative forces, which will be negative work from friction, and the energy at the end when we're at rest is 0. Okay, so our kinetic energy that we start with, we got 1/2 mass of car A times the speed of car A, so that's V2A squared, minus the force of friction, or plus the force of friction, which is going to be negative. Okay, and the force of friction is mu times the normal force, which the normal force here is just its weight, and then its work is force times distance, so that's multiplied by dA, and that equals 0. And in this equation we know everything except for VA, so we can solve for V2A right there, and once we get that, that's the answer to A, and we can use it up here. And then we can do the same exact thing for car B. So car B has very similar energy, right? So if we look at the same equation, that's a B here, same equation, it starts with initial kinetic energy, has work done by friction, and that's equal to 0. So we got 1/2 mb times v2b squared minus mu normal, which is the weight because it's on flat level ground, so that's m. I'll write that a little neater. So that's the mass of B times gravity times its distance equals 0. And once again, you can solve for V2B. Once you get V2B, you'll come back up here and you'll have V2B, and then you can solve for the initial velocity. Oh man, that's a beautiful problem. I love it. Lots of different parts all working together. So try it out. Let me know if you have any questions as you try to solve. Have a box-worthy day.